Hi friends, welcome to 1 Minute Math. Today we are doing the power rule. This is the full-length explanation video, not the short little 1-minute clip, but the full explanation. This is a calculus concept. We're talking about finding the derivative of power functions or of terms in polynomial functions by applying this shortcut rule, the power rule. Okay, so the first thing, the first thing we're going to do is just look at the power rule. It's probably given to you in your textbook or on some page of notes that you got from your teacher in this form. The derivative of x to the n, that's what this symbol means, d over dx, which you usually read as d dx. So d dx x to the n is n x to the n minus 1. Or in other words, if I said the function I'm looking at is x to the, 53rd, then the derivative of that function, f prime of x, here, n is 53, so f prime of x will be 53 times x to the 52. The old power comes down, and the new power is reduced by 1. First thing I'm going to do here before we try any examples is convince you that this rule is actually accurate. And we're going to start with our good old friend x squared. Let's say I asked you to find the derivative of x squared using the definition of the derivative. Now, if we were just using the power rule shortcut, I should say this is x to the 2, so the 2 is going to come down, 2 minus 1 is 1. I should get 2x, or 2 times x to the 1. So let's see if that holds. Using the limit definition of the derivative, and usually for power functions or polynomial functions, h goes to 0 is an easier form of the limit definition of the derivative than the x goes to a1. So limit as h goes to 0 of x plus h squared minus x squared over h. That's just the straight up definition of the derivative, and I'm going to use some algebra to simplify it. Limit as h goes to 0. I'm going to expand this square, x squared plus 2xh plus h squared minus x squared over h. And thank goodness some stuff cancels. If you're doing one of these problems and the stuff doesn't cancel, you probably are missing something somewhere. And notice how the h's, if I do h divided by h, that goes away, and that's going to take out one of those h's. So this turns into the limit as h goes to 0 of 2x plus h. Now, if I let h go to 0, that is 2x, just like I expected. Woohoo! And now you're like, that's great, lady, but that was just x squared. How did I know that that would work for x to the 53rd or x to the 56th or whatever I did in my first example? Let's just do one more. We're going to try one more of these. I have Pascal's triangle here to help us expand our power function. I'm going to do the same setup, limit as h goes to 0 of x plus h cubed minus x cubed over h. And in order to expand that x plus h cubed, I'm going to use Pascal's triangle. This becomes limit as h goes to 0 of x cubed, 1x cubed, plus 3. That power goes down by 1, x squared, and I introduce an h. Next coefficient is 3. 3, that power goes down by 1, this power goes up by 1. And the last term would be 1 times h cubed minus x cubed. This whole thing from there to there was all this, all divided by h. I'm going to cancel. X cubed minus x cubed. H. Limit as h goes to 0 of 3x squared plus 3xh plus, oops, that should be h squared. H squared, if I plug in 0 for the h's, that goes to 0, that goes to 0, and I get 3x squared. That is exactly what I would have expected using the power rule. Now, there's a reason why I've got Pascal's triangle up here, not just for expanding the cube, but do you see what happens here? All of these terms have an h in them. All of these terms have an h in them. If I would have expanded x plus h to the 4th, this x to the 4th term would cancel with the minus x to the 4th term on the end. I've got at least one h in all of these. And in fact, I've got exactly one h in this term, which would be 4x cubed h. The rest of these have more h's. If I expanded x plus h to the 4th, it would then say plus 6x squared h squared plus 4x h to the 3rd plus h to the 4th, right? All of those h's. So when I cancel out the h in this green, what I've done here in green by canceling out these h's, that's going to cancel out this h, but leave at least one h in the rest of these terms. Then in the step when I plug in 0, that's 0, that's 0, that's 0. The only term I'm left with would be 4x cubed, or in this case, 5x to the fourth, or 6x to the fifth, and so on and so forth. And we can see that in like the 101st line of Pascal's triangle, I'm going to have a 101x to the 100th. That's the term that's left after everything cancels, and that's why the power rule is what it is. So how does this play out? Let's just try a couple examples. First here, I've got a number, I've got a coefficient time, so I know that I just leave that constant cling on. I've got a constant multiple, he just stays. And then x to the fifth, if I apply the power rule, would be 5x to the fourth. And I'm going to do this a while down here. I'm going to simplify as we go. So that would be 35x to the fourth. Next term, 3 times, and n is 4 here, so I've got 4x to the third. It doesn't matter what this number is, he just hangs on. The number on the top, the power, is what comes down and then changes. So this would be 12x to the third. Now this last one, you probably know that the derivative of x is 1, but let's just play this out as the power rule. All right, so I've got a negative that stays on as a constant Klingon. 1 comes down, and then x to the 0. Well, would you look at that? X to the 0 is 1, and indeed I have 1. That's my derivative. Nice. Power rule makes really short work of these things. The great thing about the power rule is that it is super applicable, more applicable than you might think. Because if you're looking at this thing, maybe you've seen the product rule or quotient rule yet, and you look at this and you're like, oh, I hate the quotient rule. This is a fraction. I have to use it. You actually don't. If you're clever, you can rewrite something like this as a single power. Instead of 1 over x to the third, I see x to the negative third, and I can apply the power rule. The derivative of x to any one power is n x to the n minus 1. Okay. So I bring my negative 3 down, and negative 3 minus 1 is negative 4. Just be really careful with negatives and fractions that you're not accidentally going the wrong way. A lot of kids would see this and say, oh, negative 3x to the negative 2. It's minus 1. It's not closer to 0. It really is minus 1. This would be another example. And square root, in fact, let's do square root. We'll come back to this guy, but let's do square root first. You're going to see square root a lot. Square root x, I don't have to do anything bizarro with. This is just x to the 1/2, and I can apply the power rule. Y prime would be 1/2 x to the, it's 1/2 minus 1. That's like 1/2 minus 2/2, negative 1/2, negative 1/2. If you want to make this look pretty, the negative 1/2 power is like divided by square root x. So the derivative of root x is 1 over 2 roots of x. That's a good one to memorize. If you have a little room in your brain to memorize a few, that's a good one to know. Now let's deal with this 5th root of x. That would be x to the 1/5. The moral of the story here with all of these, and we're going to do one more example after this, is when you see a function, especially if it looks like a polynomial or something that just has like powers or roots or something, instead of running to the limit definition or applying the product rule or applying the quotient rule, ask yourself, can I write this as polynomial terms or x to the power terms? Because if you can, then you can apply the power rule and it's much, much easier. Yeah, so here we would have x to the 1/5. The derivative of that with the power rule would be 1/5 x to the negative 4/5. I'll let you check my computation on that one. Last but not least, something like this. Again, the moral of the story is, can I use the power rule? It is worth asking yourself that question. And in this case, I definitely can. This is a fraction that I can break up if I just split up that denominator, right? Or like use the denominator twice. You notice you can't do this if there's a sum in the denominator. You can't break it up like that. But if I have terms in the numerator over a single denominator, I can just split it up as multiple fractions. I'm going to use the exponent rules I learned way back in Algebra 1. The numbers here would reduce to 7/4. 2 minus 7 is -5. And then on this guy, I've got 5/4 x to the 2. Now, this is disgusting. Like, I'm not going to say this is a really pretty function and I'm super excited to take its derivative, but it's at least manageable because now I can just use the constant product rule, 7/4, and then my power rule, -5 x to the -6. In this case, 5/4 times 2x to the 1, so I'm not going to write the 1. Yes, you can combine the numbers here. Yes, you can simplify them. The moral or the rule of thumb here, if you're in AP calculus, would be don't. Unless your teacher's real picky about it, resist the temptation to simplify any further. That's not just because we want to encourage you to be lazy or whatever, that what we want to test here is your ability to do calculus, not your ability to simplify things algebraically. And furthermore, as a teacher, I really appreciate seeing an expression like this because it shows me the steps that you did to take the derivative. You're not just reporting an answer, you're illustrating how you got that answer. I can see the constant product rule. I can see the power rule played out. And I would rather see that than see negative 35 over 4x to the sixth. I mean, yeah, I could get there, but hopefully your teachers have that mindset. If you're a college student and your professor really likes things simplified, understandable, follow what they would like you to do. But otherwise, hopefully your teachers have a like mindset as me, and they prefer things seeing in this like expanded, unsimplified form. All right, I need to stop talking. Hopefully you found this helpful. Check out my other videos, and thanks for watching.